All right, so here is an Astrocompass. Let's look at the different things it's got. So this spins. That's for adjusting your bearing relative. There's your true heading relative to north. In this case, I'm just going to slide it directly so that north is our heading. Let's see, over here we have, this is latitude. That's your tens, and then the single digits are here. We're at 42 degrees latitude, so I'm going to turn that to, that's 40, and then it says 41 right there. So I'm going to turn it to 42. All right. And then this thing is declination. We'll get into that in a minute. It's a declination of the sun. In this case, we'll be using the sun for sighting. It's somewhere around in the 20s, I think, based on what I remember. So I'll put it there for now. This thing, LHA, is local hour angle, northern latitudes. And then you can see here, if you can read it in there, the red is for southern latitudes and the white is for northern latitudes. Local hour angle is essentially your longitude from Greenwich, or where universal time is recorded. So, and we're going to look that up in an almanac. So you look up in the almanac this, you look up the declination, and then you'll put this down. You make sure it's leveled. There are two leveling knobs, one there and one there. You make sure it's leveled. Dial in your local hour angle or your longitude, and then sight. In this case, we'll be using the sun. There's two ways this sighting thing can be used. If you're looking at a star, you look through here and there's a little magnifier there. You can't do that with the sun because you burn your eyes, which is why we're using the shadow. All right, so normally I'd use the aviation almanac, but I don't have that. I have the nautical almanac, which is actually more precise than what we actually need. So I'm doing this on the 14th of June, 2023. So we look down here, its local time is noon, but that's, what is that, 12 o'clock, so 13, 14, 15, 1600 on the, there, see my finger, 1600 on this date, and you read across, so it's 59 degrees. This is the GHA, which is the Greenwich hour angle. So 59 and 55 minutes and 0.7. But we don't need to be that precise now. But let's look over here. You look over here, you got the 20, this is the declination, because see what we're doing, we're looking up here. So you got the GHA and the declination of the sun. So, what was it, 1600? It is, you read up here, 23 and 16.3. You can see it doesn't really change, 16.2, 16.3, 16.4. We're also not going to be that precise on the Astrocompass. So 16 and a little bit is going to be fine. Speaking of math, because there are 360 degrees in going around the Earth, there are 24 hours. If you do the math, 1 hour of time gives you 15 degrees in that 360. So, and you can see that here. So this number was 59, where are we? 59 and 55.7 at 1600 hours. If we go to 1700 hours, it's 74 and 55. So just under 15 minutes in time. So that's going to be handy for interpolating this, because again, we don't need to be this precise. So we'll start assuming it's almost 59, 55, call it almost 60, and then we'll add, for every 4 minutes past noon, we'll add another degree. All right, so let's dial some things into the Astrocompass. So this is our actual location, 41.928 degrees by minus 70 or west 70, 0.0576 longitude. So we're going to approximate that and make this a little easier, 42 degrees, and by call it 70, minus 70 or west 70. Okay, universal time, 1600 hours. It was 59 minutes and 59 degrees and 55.7 minutes, which we're just going to round up to approximately 60 degrees. Again, doesn't have to be so precise for the Astrocompass. 74 degrees, 55.5, we're going to round that up to 75 degrees. And again, you'll notice there's a 15-degree difference in that 1 hour time difference, because if you go 360 degrees around the world and you divide it by 24 hours, you get 15 degrees per hour of time. And then over here, look at the declination, 23 degrees, 16.3 minutes, or 23 degrees, 16.4 minutes. Again, this is doesn't need to be very precise. We're going to just call this 23 degrees, and I'm going to call it a quarter. It's not quite a quarter, but it's already probably more precise than we really need to be for this. And then the way we figure that out, I've already dialed it in here. You can see each hatch mark equals 2 units, so you're really going between, you're trying to extrapolate somewhere between a little more than halfway between the 2 and 4, and that's for your declination, which is that. Now your local hour angle is the same as your longitude, so for us that's minus 70. So if you look here, it's either 60 or 75 depending on what time it is. It is 12:54 right now. So if you do the math, if you did, if it's 60 degrees at noon, and then 40 minutes in, that would be 10 more degrees, 40 minutes of time. And then 56, which is coming up in just a moment, that would be an additional 4 more minutes. So you got 60 plus 10 plus 4, that's 74 degrees. And we're subtracting 70 minus 70. So that's 4 degrees for our local hour angle right now. So, and then you look on this, we're in the northern hemisphere, so we're using the white. And we go to local hour angle, and we turn this, and each of these units is 2. So I'm just going to go 2 units, which is 4. And now we have to level this. Got to move fast because things will change. All right, so that's mostly level. And then what we're doing is we're lining this up, this shadow on that line. And so now that I've kept our true heading lined up to north, so that's actually true north. Or perhaps that is because of the shadow. So, and then as time moves, I would have to change the local hour angle to correct for that. Now, if you were in an airplane, this bottom part would be fixed to the aircraft. So if you were flying this way and you had to twist this to get this to line up, then you'd read this, and that would be your heading relative to true north.